Overview of classical physics. Classical physics refers to the set of physical theories that were developed before the advent of quantum mechanics. It includes concepts like Newtonian mechanics, electromagnetism, and thermodynamics, which describe the behavior of objects on a macroscopic scale. Classical physics operates under the assumption that objects behave predictably and deterministically. Overview of quantum physics. Quantum physics is the branch of physics that deals with phenomena on the microscopic scale, such as atoms and subatomic particles. Unlike classical physics, quantum mechanics introduces concepts like wave-particle duality, uncertainty, and superposition, where particles can exist in multiple states simultaneously until measured. Deterministic versus probabilistic. One of the key differences between classical physics and quantum physics is the nature of predictability. Classical physics is deterministic, meaning it predicts the future behavior of objects precisely given their initial conditions. Quantum physics, however, is probabilistic, meaning it can only predict the likelihood of outcomes, with the exact state of a particle being uncertain until measured. Behavior of objects. In classical physics, objects are treated as solid, discrete entities that follow predictable paths and interactions. In quantum physics, particles such as electrons are described by wave functions and can exhibit behaviors like interference and tunneling, which are not seen in classical mechanics. Nature of light. In classical physics, light is treated as a continuous electromagnetic wave, and its properties can be described using classical wave theory. However, in quantum physics, light also behaves as a particle, called a photon, exhibiting both wave-like and particle-like properties. This duality is fundamental to understanding phenomena like the photoelectric effect. Scale of observation. Classical physics works well for large-scale systems, like planets, cars, and everyday objects, where quantum effects are negligible. Quantum physics, however, is essential for understanding the behavior of particles at microscopic scales, such as electrons, atoms, and molecules, where classical physics fails to provide accurate predictions. Concept of energy. In classical physics, energy is continuous and can take on any value within a given range. In quantum physics, energy is quantized, meaning it can only take specific discrete values. This is seen in phenomena like atomic transitions, where electrons move between fixed energy levels. The uncertainty principle. The Heisenberg uncertainty principle is a cornerstone of quantum physics, stating that it is impossible to precisely measure both the position and momentum of a particle simultaneously. This is in stark contrast to classical physics, where such measurements can be made with arbitrary precision. Wave-particle duality. Quantum physics introduces the concept of wave-particle duality, where particles can behave both as waves and particles depending on the experiment. This was not part of classical physics, which treated waves and particles as distinct entities with separate behaviors. Conclusion. Classical physics versus quantum physics. In conclusion, classical physics provides a framework for understanding the physical world on large scales with predictable and deterministic laws, while quantum physics addresses the unpredictable and probabilistic nature of the microscopic world, where particles and energy exhibit strange and counterintuitive behaviors.